This is Module 12, Lecture Notes 23. Today we're going to be talking about gases and pressure. And so the first thing we want to do is define the word pressure. And here I've written that pressure is just the force per unit area exerted on an object. And that also can be written as force divided by area. Okay, that's kind of a general definition for pressure. But today we're going to be talking about pressure specifically with gases in mind. And I love this unit and this topic because gases are all around us. And they are something that are very common to be able to relate to everyday situations. Okay, the air around you is a gas. You encounter many gases as you're cooking, as you're bouncing a basketball, as you're opening a bag of chips, opening a bottle of pop. I'll give you some examples as we go throughout the lecture, but you should be able to find ways to relate this unit to your everyday life, which I think is really cool. Okay, so I want you to think about how gases exert pressure. So here I have a balloon and I filled it up with gas or air. Okay, and I want you to think about what is happening to the air molecules that are inside this balloon. Are they staying still? No, they are moving all about and they are coming in contact with the walls of the balloon. They are colliding with the walls of the balloon, exerting pressure. So the way that gases exert pressure is through collisions. And these collisions are going to be the main focus of what we talk about today. Okay, so think about the molecules moving around and colliding with the walls of the container, thus exerting pressure. So how do we measure gas pressure? I've listed some units for you, some of the most common ones, and I'll go through them so you know how to pronounce them. This is called pascals. You might see it abbreviated as PA, okay? But more commonly, you will see it as kPa, which is kilopascals. Okay, that just means there's 1,000 pascals for kilopascals. This is atmospheres. This one is very common, and it's abbreviated ATM. This is called torr. And this is a pressure unit, millimeters of mercury. Okay, and down here in this area, I have given you the conversions between each of these. Okay, so this is just saying that 1 atmosphere is equal to 101.3 kilopascals. 1 atmosphere is equal to 760 torr. 1 atmosphere is equal to 760 millimeters of mercury. Okay. All right, moving on to the next section, we're going to talk about how you can influence or how you can change gas pressure. We're going to talk about what variables would have an effect on the pressure. Okay, and I've listed them here for you. I think the most helpful thing when thinking about these variables is to use visual aids. So let's say I have this container and I'm going to add some gas to it. And my gas today is going to be these yellow beads. Okay, so the pressure is measured through the number of collisions on the walls of the container. And you can hear that. We will be measuring it with our ears. Okay? So if we're talking about the temperature of our gas, if my gas is just moving around in my container and I want to change the temperature, let's say I want to raise the temperature, okay, I would do that by making my particles move faster. Okay, so you can automatically hear that as the temperature goes up, I have changed the pressure of my gas, okay? Because there's more collisions on the walls of the container. So for temperature, I want you to think in your mind about the speed of the shaking beads. Okay, think temperature is related to the speed that my atoms are moving in my container. Okay, so let's go on to volume. All right, so I have this first container and I have my particles moving in there. To show that I want to change the volume variable, that would mean that I'm changing the amount of space the beads have to move around. Okay, so let's see if we can notice that effect. So the beads are moving in a smaller container. The beads are moving in a larger container. So when you think of volume, I want you to think of space of the container. You could draw a small one, you could draw a large one. That way you have that in your mind. Okay? And then number of moles simply is just how much gas is in my container. So I can start with some. Okay, you can hear it moving around. And I want to add more gas. Well, I think you get the idea that of course the pressure is going to be affected because I have so many more collisions with the walls of the container. So for this one, I want you to think about number of particles or beads. Okay, so hopefully that helps you visualize how these variables are going to be affecting our collisions, which are in turn going to be affecting our pressure. Okay, so in the next section, we're going to look at a couple of these variables. And there were a few scientists that studied gases. They studied gas laws. And the first one is a guy by the name Boyle. Okay, he looks like this, and he said that pressure varies indirectly with volume. Okay, so what that means is that when one variable increases, the other one should decrease. So he would say as volume decreases, pressure should increase, and vice versa. And what that would look like is you have a container, and let's say we have 10 molecules moving around. 4, 5, 6, 7, 8, 9, 10. Okay, well now I have the same 10 molecules, but they're in a much smaller container. Okay, so when you look at this in terms of pressure, if I decrease the volume of the container, the pressure should go up because there are going to be more collisions with the walls of the container because they have less room to move. So we can write it this way. I have a high volume, I have a low pressure. Okay, I have a low volume, I should have a high pressure. They are indirectly related to one another. Okay, and that should be the same as this visual that I showed you earlier. In a larger container, you have a lower pressure. In a small container, you have a very high pressure. Same thing with a balloon. When the atoms have lots of room to move around, the pressure is low. If you try to squeeze the balloon to decrease the volume, well, I think you all know what happens. The pressure becomes so high that the balloon pops. Okay, so those are some visuals for you to remember for Boyle's law. And the way that we would write that is that pressure and volume remain constant. Pressure times volume equal a constant. So when one goes up, the other must go down in order to remain constant. Okay, the second law we're going to look at is Charles's law. Here's Charles. And he says that volume varies directly with temperature. So that means that volume and temperature have a direct relationship. When one goes up, the other goes up. When one goes down, the other goes down. That is a direct relationship. So let's fill in these sentences here. As temperature decreases, volume decreases. I bet you've experienced this one before. Have you ever gone out to your garage in the winter and the basketball or the kickball is flat? Okay, as the temperature goes down, the volume goes down. Or maybe your bike tires are flat in the winter. Okay, the molecules are moving much more slowly at a low temperature, and so they're not exerting much pressure on the walls of the container. On the flip side, if the temperature goes up, the volume goes up. Okay, so now the molecules are moving much faster. Have you ever left a bag of chips in a car on a hot day and it expands? Why they tell you to keep spray paint out of high temperatures, because things expand when they get hot. Okay, the equation for this would look like volume over temperature is a constant. Okay, so when one increases, the other must increase in order to remain constant. Down at the bottom of your paper, I also want you to note that pressure and temperature are directly related as well. So when pressure goes up, temperature goes up. When pressure goes down, temperature goes down. And this is another law. We're not going to spend a lot of time focusing on it, but you should know that they also have a direct relationship. Okay, on the back of your notes today, we are going to combine those gas laws that we just talked about into the combined gas law. And this is what it looks like. It says P1 V1 over T1 equals P2 V2 over T2. These variables here I like to label before. And these I label after. Okay, so what this means is that when we have a changing set of conditions, we can plug in what we know to be true before, and we can see what happens after the change to our variables. Okay, when you are using the combined gas law, there's a couple things you have to keep in mind. The temperature must be in Kelvin. So before you plug in a temperature to this, you need to remember that you take your degrees Celsius and you add 273 to convert to Kelvin. The other thing you need to note is that when you're plugging in pressures and volumes, you need to use units that match. So what that means is if I'm using a pressure in atmospheres for my initial set of conditions, I need to be using atmospheres for my final set of conditions as well, because my units need to cancel. Same thing for volume. If you're using liters, then this should be in liters as well. They need to match. Okay? And then lastly, I want you to write off to the side this note. If a variable doesn't change, get rid of it. Okay, and I'll tell you what that means as we work through our first problem together. so let's jump into an example. We have a balloon, okay? It has a volume of 785 milliliters on a fall day when the temperature is 295 Kelvin. So they've given us the initial set of conditions for this balloon. It's fall. This is the temperature. Now it's winter and the temperature falls to 273. What is the new volume? Well, we should know enough from our discussion on the first page that volume and temperature are directly related. Okay, remember with Charles's law, we talked about that if the temperature is going to fall, then the volume should get smaller as well. So we should keep that in mind when we're solving this to make sure that our answer makes sense. But they want to know what the new volume is, and we can actually find that with a number using our combined gas law. Notice that they did not mention pressure at all. So we are assuming that pressure doesn't change. We don't need to account for it in our equation because it's remaining constant. So I'm going to use the equation V1 T1 equals V2 over T2. I got rid of the pressure variable because we're just focusing on volume and temperature and how they're changing in this problem. Over here in the box, I want you to get into the habit of writing out what you know. V1 is my starting volume, 785 milliliters. T1 is my starting temperature, 295 Kelvin. V2 is the new volume. We don't know that, so I'm going to put a question mark. And T2 is the final temperature. They told us that it falls to 273. Now we're ready to plug into our equation. I didn't have to mess with the temperatures because this first problem put them in Kelvin, so that was kind of nice. But if they wouldn't have been in Kelvin, you would have needed to switch those beforehand. So this is what my equation looks like. I'm solving for V2. Now let's do a quick review of how we solve a problem like this. I like to use cross multiplication. Okay, so what that means is you're going to be multiplying 785 times 273, and you're going to set that equal to this other side, V2 times 295. Okay. I guess I didn't do a very good job of keeping units on this. Sorry about that. All right, so now we need to get V2 by itself. And I think this looks more like a problem that you guys know how to solve. If I want V2 by myself, I need to divide by 295. So let's plug that into our calculator. I would have 785 times 273. I'm going to press equals divided by 295. And I should get 726.5. What label should I put on this if it's a volume? My initial volume was in milliliters, so my final volume will come out in milliliters as well. And that's my answer. You probably do want to ask yourself, does that make sense? My temperature went down, my volume went down. The balloon got smaller as the temperature went down. The molecules started moving more slowly. That makes sense to me. Okay, so let's read through this second problem. I'll get you set up with the variables and then I'm going to let you solve it. It says a piston has a volume of 1,580 milliliters at 273 Kelvin and a pressure of 758 millimeters of mercury. So those are my initial conditions. The volume is going to change to 5.3 liters. What is the new pressure? Now notice they never talked about the temperature changing. Okay, this doesn't change. So that should simplify your equation quite a bit. You're going to be able to leave the temperature out of this problem and use the equation P1V1 equals P2V2. If something doesn't change, cross it out. Now, before you begin plugging things in, I want you to do a simple scan of your variables. Do your pressure and volume units match? Well, pressure, you only have one of them, so you know that the answer will come out in millimeters of mercury, and that's fine. But when you look at your volume units, one is in milliliters and one is in liters, and those don't match. It doesn't matter which way you go, as long as they're the same. I'm going to switch this to liters by dividing by 1,000 or moving 3 decimal places to the left. So that's the same as 1.58 liters. Okay, and now I think you're ready to plug in and solve. I would like you to solve for P2, and then I want you to flip over to the first page and make sure your answer makes sense with one of the gas laws that we learned earlier in the lecture. Okay, I've plugged in the variables for solving for P2, which means I need to divide by 5.3. So I'm going to take 758, you see that, times 1.58, press equals, and I'm going to divide by 5.3. And I get 225.96. So let's just call this 226. Because my first pressure was in millimeters of mercury, my second pressure should have the same unit. Does this make sense? And what law is this that tells you that it makes sense? Okay, my pressure went down, my volume went up. Okay, so that is the gas law that says when I increase the amount of space that my atoms have to move, the pressure should be lower. It does make sense, and that is Boyle's law here on the first page. All right, go ahead and start on the third problem. See how far you can get. Notice that your temperatures are in Celsius, so you'll need to do some conversions, and then come back and check your answer, please. Okay, for this last problem, all of your variables are changing, so you cannot eliminate anything from your equation. I have P1, V1, make sure you switch your temperature to 298 Kelvin. I have P2, we're solving for V2, and make sure you switch your T2 to 373 Kelvin. I went ahead and plugged everything into the equation, and we are solving for V2. Now, it's important to stay neat when you are cross multiplying with this many variables. I'm going to do this direction first. So I will be taking 1.5 times 1 times 373. I'm multiplying all of these things together. And I'm going to set that equal to the other side. 6 times V2 times 298. Okay, you're multiplying this side, setting it equal to that side. That's what cross multiplying is. Okay, and then in order to solve for V2, you just need to move your variables down to the bottom. So we're going to divide by 6 and divide by 298. Okay, and that will leave V2 by itself. What that would look like in your calculator You take 1.5 times 1 times 373. I would probably press equals after that, and then divide by 6, press equals, divide by 298. Remember, these blue calculators are really picky about how you do this division here. You want to divide by 6, divide by 298, so it knows that you want both of those in the denominator. And I get 0.31 for my answer. V2 equals 0.31. 0.31 what? It's a volume. My initial volume was in liters, so my second volume will be in liters as well. Okay, I hope that helps you guys work through some of these tougher problems. You will get a chance in the lab to explore how these gas pressures are related to each other when you change the variables, and I hope it's a lot of fun. See you guys next time.